Okay, thank you. My name is Sujoy Ganguly. I'm head of the Applied Machine Learning Research group at Unity. I'm going to talk to you today about our efforts around using synthetic data to train models that are performant in the real world. As I'm sure everybody here knows, training with real world data is challenging. Getting real world data can be expensive, time consuming to collect and annotate. Sometimes it can be biased and insufficient, requiring us to re-annotate or recollect data. And often, particularly in human-centric tasks, can be privacy non-compliant. Typically, a computer vision workflow for acquiring real-world data and using it will go acquire real-world images, get it labeled and annotated, train the CV model, evaluate the model, and deploy the model. And then comes the nightmare of anybody who's done these things in production, which is, in evaluation, we realized we didn't have enough data or the right kind of data, so we have to go back and acquire more data, relabel it, retrain it, evaluate it. Or the real nightmare for anybody, which is, I deployed the model, it's live in production, suddenly all kinds of things are going wrong. Oh no, my data was problematic. Let me go back and fix my data, reacquire it, retrain it, which is a slow process, right? This can often take 70% of your time, at least, is just in collecting and labeling the data. And some people might tell you it's even more than 70%. It might be closer to 80, 90%. So these data pipelines are very, very critical. Now, synthetic data, in principle, can alleviate both some of these workflow challenges as well as data collection challenges. And in that condition, what you would write, so synthetic data in principle can come auto-labeled. It can be privacy compliant because it's all synthetic. It's easy to iterate on in principle. It's affordable, so small teams can generate massive amounts of data sets without having to spend huge amounts of money on labeling and data acquisition. And it can be representative. You are able to control, in principle, aspects of your data to represent your target data sets. The workflow, though, looks quite different. Well, not quite different, but has some key differences. One, you have to build an environment from which to generate that data. Then you generate the automatic data, the auto-labeled images. You can train your model, you can evaluate your model, and you deploy your model. But here, you can iterate in many other places programmatically. So when you do your evaluation, if you're finding that your performance isn't good, you can either go update the data that you've generated, change the distributions of the data, alter the manifold. If you realize you haven't included some content that you would have liked to detect, like you're like, oh, I would have liked to have also detected chairs, you can add them back into the environment programmatically and generate more data. When you go deploy, if you're finding that there's biases or performance or edge case problems, you can go regenerate the data either by altering the parameters of the environment, generating more data, altering the label spec of the environment, or if in the case where you are just missing certain content, you can always update the environment. And these things can be done in a sort of programmatic way. And so your data pipelines become code rather than lots of complicated, go talk to an annotator and explain to them what you mean when you say, I'd like this semantically segmented, and try to write down very careful rules. However, synthetic data comes with one obvious problem, which is it's synthetic. It's not real data, and you need your model to perform well in the real world. And one of the ways to bridge this so-called sim to real gap is through a technique called domain randomization. So domain randomization essentially asks us to create the most diverse data set that a model can learn by varying as many of the properties as we can of the simulation, often in wild manners. So for example, we might alter the spatial location and orientation of our groceries objects that we want to detect in our maybe inventory stock application. We could vary the color and texture of the background, the lighting, the optical occlusions, et cetera, et cetera. And suddenly you're presented, because this is synthetic data and it's programmatic, with all the things that you need to vary, and that's actually itself overwhelming. And in my team, we kind of break these variations into two types, particularly for object-oriented tasks like object detection or semantic segmentation. And that's intrinsic variations, which would be the variations of the target object, like shape, texture, color. And they can vary from simple variations, like you're just trying to change the color of the object, so you're just swapping the color out, to more complex, like you're trying to perturb the shape of the object. You're trying to add creases or crumples, or you're trying to rig the object. The object is animatable, posable. Extrinsic things are things like that are related to what you might call the environment. So they relate to things like where the camera is placed, how the objects are placed in the scene, their orientations, the lighting, all these sorts of things. And they can span from structured, so that is to say, these things are all very interrelated and there's a lot of structure in the scene, to unstructured, where you can just vary them independently and wildly and it doesn't matter. Examples of tasks that might fall in here. So imagine you wanted to detect a specific shoe, like a white Air Force One Nike sneaker. That's a very narrow class. So we might say the intrinsic variations of that class are quite narrow and simple. And we don't really care about the environment. We're not trying to detect it in a warehouse. We're just trying to detect it generically. So we might believe that the extrinsic variations could be unstructured and wide. Conversely, if you're trying to detect a wide range of broader class, like the class of all shoes or even all sneakers, suddenly you get into a place where you go, well, what defines the variations of a sneaker? And you go, oh, that's a very wide class. Again, maybe you don't care about the context. So you say, well, I can use an unstructured background environment. Oops, sorry, I hit the wrong button. Another example would be saying detecting furniture sets. Well, because it's a set, there's inherent structure. They're all related to each other. Though the variations may be simple, you might just be swapping out materials or colors. Maybe the most complex version of this problem, though, is detecting people in specific environments, where you have to care a lot about the environmental structure and variations, as well as the intrinsic variations of people, which are reasonably broad, right? We have so many very subtle, very key variations in people, from hair, poses, skin color, clothing, all those sorts of things. And so this means that these kinds of variations that you're trying to put into your simulation to generate your synthetic data sort of put a burden on your content. And in fact, they really put a burden more on your content than they do on your rendering pipelines. It is the content that is sort of king in this problem. And again, we sort of break up, roughly speaking, content into sort of 4 dimensions. We have the visual, which is that your content renders correctly in a wide variety of conditions. The assets are free of defects, and the appearances can be varied. You then have sort of the physical, the assets that you're putting in the scene have accurate colliders, means they don't intersect with each other. The masses and densities and friction coefficients and other material properties can also be varied. Kinematics, the objects move according to according to animations that make sense, that these animations can be shared across common objects in the scene and be varied. And then lastly, of course, maybe the one that we are all most familiar with is the fully embodied version of content, which is like the way we experience content in the real world, which is that it can react to the actions of agents, e.g. us. It can be picked up and moved by things in the scene. So for today's talk, I'm going to focus primarily on the visual and the touch of the kinematic, and not so much talk about the physical and embodiment, except maybe a little bit at the end. So most of the time when we're doing computer vision work, we're thinking about those visual aspects. And there we think about 2 things. There's the meshes, which is what controls the shape of the object, let's say. And then there's sort of the UV, which controls the texture channels that we attach to the object. So meshes have to be coplanar, laminar, faces have to have good zero area, non-manifold geometries, all these sorts of things. So these are all computer graphics things that you need to create meshes that will render properly in many scenes. The other thing you need is that the material channel properties, so that's like the albedo, the texture, the specular, the normals, the surface normals, all have to be independent and distortion free. Now, this is a lot of, right up to here, we've talked a lot about the huge burdens of content. And this seems like a massive barrier for anybody wanting to work in synthetic data, that you have to suddenly create all this technical art. And that is so hard. And most people in computer vision are not experts. And I would imagine there's a lot of people on this call who don't even know what most of these words mean. I know I barely knew what they meant 2 years ago when I started working on these problems. And to deal with that, what we are doing is releasing a human-centric computer vision data generator in which we've taken care of most of these problems for you. So in this data generator, we have a wide range of human assets that are all well-behaved. Their meshes are free of defects. The UV channels are well separated. They have a diverse set of animations that you can attach to them, massive amount of clothing textures that can be applied, parameterized randomization of placement, orientation, camera systems, lighting systems, the presence of occluders and distractor objects, capture with a high definition render pipeline, so high quality renders, a wide range of labelers that you can attach. So you can have bounding boxes, instance segmentation, semantic segmentation, COCO key point pose labeling, as you're seeing in this picture. And all of this will be packaged for everybody in binaries that can be run both in Linux and on Mac, plus CLIs and configs so that you can run these programmatically in the background. So these are headless renders, in fact, that we are packaging for everybody. So let's go through. So this is a cool data generator, but and here you can sort of see, hopefully it's playing. Are people able to see the video okay? Okay, hopefully so. Hopefully so. In this, yeah, okay, good. In this video, we're just playing back a bunch of different frames that have been rendered with instance segmentation and pose labels on the objects. So let's start through all the different randomizations we're trying to provide. So one, some of them are obvious, like camera placement randomizer and position randomizer. Some of them might be odd and unusual and new to people in the field. So the animation or pose randomizer basically allows us to vary the poses of the characters or people in the scene sort of by sampling a random frame of an animation at any time. So that's what you're seeing here. So we have a 28 different animations that can be applied to any character. They can be played in sequence, but you can also grab a random frame from them and therefore get anybody to pose in a very diverse set of manners. We have the clothing texture or shader graph randomizer. Here we're actually altering the UV channel so that we can alter the clothing, and the clothing is all separated out top and bottom masks, so you can change the shirt separately from the pants, and that's what you're seeing here. You can also alter some of the surface normals as well, allowing you to add wrinkles to the clothing as well. As you're sort of seeing here, you can see some wrinkles being added sort of to the surface. This is all fully parameterized, so this can be controlled from the CLI as well. So you can configure these parameters and then generate these frames. So those are the two big randomizers that might be unintuitive that we've added to this system. The other ones are, as you'll see as I play these videos, they are around lighting, color, camera. And here in these videos, you're going to see pretty wild sets of poses, positions, colors, backgrounds, because we are just sort of splitting the system uniformly sample from everything that we've provided. So the widest range that we can provide. And hopefully these videos play. I know over Zoom things can be a little bit strange, but here you're seeing the RGB captures and the labels on the other side, the label data on the other side. Okay. So again, to go walk through how these are being randomized. So we have the intrinsic variations that we're providing. So we have placement, scale, rotation, animation. We also have in every one of the objects the ability to change the texture. The hue offset means the sort of color perturbation that you can apply. So for every texture, you can add or subtract a little bit of the hue so that you can get extra perturbations. You can vary the albedo textures, the normal textures, the mask textures, the material textures, the top and bottom clothing, all independently. So for every character in the scene, as well as every occluder object, which are just object primitives that we put in the scene to create occlusions and distractions. Okay. In terms of the extrinsic parameters, or those that are related to the rendering, you have the lights. So that is the sun angle. So that's like the horizon light, the light that comes from infinity. You also have a set of 6 lights whose intensity and color, position, and rotation you can change, as well as you can turn them on and off, any set of them on and off at any time. The camera, you have the field of view, the focal length, the position, and rotation of the camera. And then we also have some post-processing effects that are enabled. That's like vignetting, which is like putting the cool blur on the edge that you get in a lot of cameras. We have the exposure, white balance, temperature, depth of field, color adjustments, and saturation adjustments for contrast and saturation as well. Okay, so with all those randomizers, and here I'm showing you distributions of object number and object size using the default parameters of the randomizers. In other words, the widest range that we can put into the system and get it to run. So, and I'm comparing them to the COCO data set, the COCO persons data set. So here on the, well, I don't know which side is which, but on one side we have the probability of the number of people in an image. So we see, say, for example, in the COCO, we have mostly 1 or 13 or 2, 1, 2, or 13, or the distribution of numbers of people. With our default parameters, you get a much smoother distribution of numbers of people in the scene. Additionally, with our default parameters, and all these are changeable, so they can be tuned as needed, we tend to have, on average, slightly bigger people relative to the overall image size. Additionally, you have this controllable placement of people. Here, I'm showing you a heat map. Oh, there's a label missing. On the left, on my left, which is the one with the smaller heat map, that is COCO. Here, what we're overlaying is the bounding box locations in every frame. You'll see a slight aliasing effect because not every frame in COCO is the same size. But by and large, you're seeing that in COCO, the objects are roughly centered and don't quite extend all the way to the edges of the images. And a similar distribution of behaviors is got with our default parameters, which is the images on the left, which is the synthetic data. There, you don't see this aliasing effect because all of our frames from the synthetic data are the same size. Okay. We also have, as we talked about, these pose randomizers that allow us to vary the poses. Again, on the left, we have COCO in red, and on the right in blue, we have synthetic. Here, I'm just showing 5 key points: the nose, the 2 wrists, and the 2 ankles, rather than showing all of them, because then it gets too many heat maps at once. Here, what we've done is we have centered the every pose, and you by finding the mid-hip point and making that 0, 0. We have then used the torso length as the unit of measure of 1, a distance of 1, and then plotted a heat map of every key point in that coordinate system. We see that in COCO, unsurprisingly, that there is a pretty diverse set of poses. However, there is a certain anisotropy. They are basically front-facing. So we have sort of a stage right, stage left thing going on here, where mostly you see them having that right-left symmetry breaking. In the default set of parameters in our data generator, you have more diversity of poses. And you also break this symmetry because you can rotate you randomly rotate the objects. So you have as many images from the back as from the front. Okay. We also have a little more improvement of label consistency. So people who are very familiar with the COCO dataset and many real data sets know there's a lot of frames that have people in them where they didn't bother to label the key points because it was hard and time consuming and very, very expensive. And so that's not the case in synthetic data. In synthetic data, every frame that has a person in it has the key points labeled. However, if the key point is occluded, so here we're only showing the visible key points, you won't get all 17 COCO key points, but you may get fewer due to occlusion. And we have a uniform distribution of key point type as well, because again, we're using uniform distributions for the samplers, and et cetera. Again, all of these things, a lot of these are implicit, you have implicit control over by controlling the placement and the camera, et cetera. Okay, now comes the part that really matters, which is, well, how well does this synthetic data do on real as a training method? So for baselining this data set, what we've done is we've generated synthetic data, trained the model. We did no tuning of the synthetic data parameters, and the model was trained first on synthetic only. Then we fine-tune the model on our target real data. There's no weight freezing. We just let all the layers train. And then we evaluate all the results on the COCO test dev 2017 dataset. So we're using a basic pre-training fine-tuning scheme to baseline the performance here. Okay, so in general, we used almost 500,000 synthetic images for pre-training. In what we see is, so here we're showing the bounding box average precision and key point average precision, and we have at different amount of real data used for fine tuning. We have models trained from scratch. Trained from scratch means no pre-training. We just train on the target real world data set. ImageNet pre-training, which is taking the ImageNet pre-trained weights and fine tuning on the target real world data set, and synthetic data pre-training. In general, we see that there is an improvement of synthetic pre-training over ImageNet pre-training or training from scratch. That improvement, of course, is most dramatic in the small data limits, so 641 images, 6411 images, which is 1% and 10% of the available real-world data, and that it's a bit of diminishing returns. As real data gets larger and larger, it sort of closes the gap. And this is true both in our bounding box and key point systems. So this really means, not surprising to anybody, that with more data, we're getting rid of false positives. So here in the top row, we have the images with ImageNet pre-training and 6,411 COCO fine-tuning. We see that we get false positive bounding boxes that are removed when you have synthetic data as pre-training. And we have some refinement of the pose models themselves, cleaning up some of those things. This is just in agreement with the fact that the key point and bounding box precision improved. Now we get to the truly interesting stuff, and sort of almost previewed by Matthias that, ooh, but zero-shot performance is terrible. Okay, so here I'm showing model. Say that again?
2 more minutes.
Yeah, perfect. I will be done right now. So here we are pre-training a model on, here we see the effect of synthetic data size on model performance. In blue, we see for key point average precision. In blue, we see the zero-shot performance. So this is just synthetic data, no real data, and we see that it's not very good. We see, though, that, of course, as we add synthetic data, as we add a little bit of real-world data, that model performance improves dramatically with synthetic data. For reference, these were the ImageNet pre-training numbers. So we can see that, as before, we are outperforming even in the small data, particularly in the small data limits. So this brings up the question of what do we do about the poor zero-shot performance? And our hypothesis is to approach this via meta-learning, in which we update the model parameters, the data generator parameters, according to model performance on a specific task. So this has been done by other researchers before in many different ways. And what we are hoping to do by mid-June next year is provide a toolbox for people to try this with this simulator, in which we will have APIs on the simulator as well as orchestration frameworks so that people can run these things themselves and try many different methods. We ourselves are trying some search methods to try to optimize this right now. We're also, I'll skip this just to say that we're also going to be releasing a object pose estimation environment for synthetic data as well. So look out for that soon. So the PeopleSansPeople benchmark and environments will be released in December. We will update that with Python APIs in March, and a whole meta learning toolkit should be available in June, all for public use. And in February, we hope to have a object pose estimation environment as well. And that's it.